Welcome back. In the previous segment, we looked at how to construct quadratic basis functions for quadratic elements and also pushed ahead to higher order basis functions, right, for higher order elements. The formula for higher order basis functions is obtained from the Lagrange polynomial formula, right, and we saw all of that. Just a couple of points I want to make about the Lagrange polynomial formula, and here are those points. So, first of all, the Lagrange polynomial formula, or the Lagrange polynomials themselves, right, they satisfy the Kronecker delta property which our basis functions have possessed. Okay, so the general formula also satisfies this Kronecker delta property, and I just want to demonstrate that. So Lagrange polynomials satisfy this Kronecker delta property. Okay, let's check it. So you recall that if we have an element with NNE nodes, we have this formula for the eighth of those basis functions, right? NA of C we found is the product B going from 1 to number of nodes in the element, B not equal to A, C minus CB divided by a product with the same limits but the term that we are multiplying here is CA minus CB. Okay, so let's check this out, right? And this holds, of course, for A equals 1 to number of nodes in the element, right? Let's check this out. So we know that from the Kronecker delta property, if we have NA CA, right, just substituting C equals CA in the formula above, we see very clearly that NA CA equals pi B equals 1 to number of nodes in the element, B not equal to A, CA minus CB divided by pi B equals 1 to number of nodes in the element, B not equal to A, again CA minus CB, right? So therefore this is indeed 1, right, which is what one would expect from the Kronecker delta property, right? NA of CA should be equal to 1. All right, let's see what happens if we take if we evaluate C at some other value of at some other position in the element in the parent domain. Okay, so in particular, let's suppose we evaluate NA not at CA but at some CC, right? Where of course we are saying here that C is not equal to A. Okay, so we have the product B equals 1 to number of nodes not equal to A. Here we have CC minus CB, right? Remember, that's a product, right, of all those sorts of terms, divided by another product, same limits, B not equal to A. Here we get C C minus, sorry, here we get CA minus CB. Okay? And now you see what happens, right? In the numerator, the product runs over B equals 1 to NNE, but B not equal to A. However, for C not equal to A, what we observe is that for one of these terms does take on the value CC itself, right? CB is equal to CC. And that's what sets this expression to 0. Okay, so we get here 0 when C is not equal to A. All right, so the Kronecker delta property does indeed check out. It's a simple enough exercise for you to check that the other property holds, right? So check that now sum over A NA at any value of C is equal to 1. Okay, using the Lagrange polynomial formula. Okay, check this out as an exercise. All right, so having looked at those two properties, let's move on. But now let's try to develop our equations, our finite element equations, our finite element formulation for the case of quadratic basis functions. Okay, so what we will do now is develop the finite element formulation with quadratic basis functions. All right, and we will take this up directly in the finite dimensional weak form. All right, and specifically we're going to take it up in the finite dimensional weak form where we've already introduced the notion of the partition into elements. Okay, so we have sum E going from 1 to number of elements, integral over omega E, WH comma X, sigma H A dx. And we recall that sigma H is what? Sigma H is given to us through the constitutive relation, which is E times UH comma X. Right? This is equal to sum E equals 1 to NEL, integral over omega E, WH F A dx plus. Let's suppose we are dealing here, and in fact let us deal with the Dirichlet-Neumann problem. So we get our traction term or our Neumann boundary term, WH T bar A. Okay, and I should mention that here we have the Dirichlet-Neumann problem. Two questions. What other kind of problem could we consider? Right, we could consider the Dirichlet problem. Another question. Why do I say that this is the Dirichlet-Neumann problem? Where does that show up? Right, it shows up in the fact that this is the Neumann boundary condition. Okay, the Dirichlet condition is, of course, already embedded in our spaces. All right, so this is the problem we are looking at, and let us now focus on this term. Okay, this left-hand side integral over the element. Right? Okay. So let's consider integral over omega e wh comma x. We have sigma h, but let us directly use our constitutive relation here. We have e u h comma x, and I've left a little space here because I want to introduce the area in there, right? Dx. Now, how are we going to write this out? Okay, in order to write this out, we need to express our gradients. Okay, right? And in order to express our gradients, what we will do is we will recall, as we've done before, that UH comma x, it is an element E because we are talking of integrating only over element over the domain omega E, but I'm going to save ourselves the writing of that extra subscript here. Okay, so I'm just going to write it as UH comma x. This is sum A going from 1 to number of elements, but we are working with quadratics here, right? So we have A going from 1 to 3. NA, and you recall that just as we did before, we are going to calculate this gradient by taking the gradient of the basis function. Okay? And a similar sort of expression for the weighting function. Okay? Where we may further ask, well, how do we compute these gradients? The chain rule is the answer, right? So the way we will write NA comma x is NA comma C, which is easy to do because our basis functions are indeed parameterized by C, right? This times C comma x. Okay, so having written out, having recalled how we're going to write out our gradients, right? The only difference here between, with respect to what we did for the linear problem is that we need to sum over 3 basis functions now because we're doing quadratics. Okay, so the way we will use this is by writing this as an integral over omega e. Now for wh comma x, I'm going to write sum A going from 1 to 3 NA comma x, but we already know NA comma x is NA comma C, C comma x, C A E. All of this represents WH comma x multiplied by EA multiplied again by sum over B going from 1 to 3 NA comma x, but again we're going to use our chain rule. It's not A, it's B here because we're summing over B. NB comma C, C comma x, D, B, E. Okay? dx. That is how we're going to compute that element integral. Right? Okay then, let's see what else we can do about this. Let's start out by computing each of these quantities. Okay? The computation of C comma x takes a little more preparation, as we know from before, and we'll postpone that for just a few minutes. All right, so let's start out here. N1 comma C is d dx of N1, but N1 we remember is 1/2 C times 1 minus C. Okay? It's that derivative, right? Which is d dx of 1/2 C minus C square, okay, which we see is 1/2 times 1 minus 2c. N2 comma c is d dx of 1 minus c square, which is well, this is easy to do. I don't need another step here. This is just minus 2c. And finally, N3 comma c equals d dx of 1/2 c times 1 plus c, and when we carry this out, we get 1/2 1 plus 2c. All right, straightforward enough. Now, what about c comma x? What about computing this term?